All right, so today was day 40, and basically today I mostly focused on graph learning. I mean, it was many things. I still not finished. Probably I will study tomorrow a bit. What did I check it out? All right, so a friend of mine gave me like this info, and I basically read this all. I'm gonna just give a quick overview of what I saw today. So we know like some basic statistical descriptors of graphs, right? For example, the some measures between centrality, degree centrality, density, transitivity. How do we visualize graphs? We try out, there are like energy-based methods, etc. What else? The graphical models, right? A little bit of measure theory, and which is like the true mathematically formally justification, right? Then also graphical models and spectral clustering, I believe, network inference, which network inference is basically we see like some output, and we trying to understand the relationship of some variables, how they relate one another to produce the output. So we assume that there is some sort of like a graph structure, and so some sort of relationship. And in essence, we compute the correlations, or the partial correlations. It depends, and we invert the matrix. We compute the precision matrix, and if it's like a high number, we draw an edge. Otherwise, we don't. Something like this. And what else? We also have a spectral clustering, which is really interesting. It's it can be established as a minimization problem. Okay, so first the motivation is that you want to I don't know, like cluster a graph. But how do you cluster a graph? Like, you want to cluster the graphs that relate to one another closely together, and cluster as a different cluster the nodes that relates together, cluster in some way, and distinguish by the other nodes that cluster in a different way one another, right? So this is an example. So we have like this graph. We can cut this graph and create like these two clusters. We can it's like a minimization problem, but this can get up exponential. We use a simplify, like a relaxation method, and so on. With linear algebra, it's like literally the easiest way to represent it. And basically, you compute something that is called the Laplacian, and with the Laplacian, it's basically the degree matrix minus the adjacency matrix, and then you compute the eigenvectors of the Laplacian, and the coordinates, like all the rows are like all the coordinates of the points, and you can perform k-means over this. But essentially, just as a summary, is a way of representing a graph, the relationships of a graph, of the nodes of a graph, into a geometrical space. And in this geometrical space, we know that we can perform like k-means. So we can visualize directly in an easier way the nodes, and we can directly cluster them. And we do them basically by the Laplacian and then the eigenvectors. And what else? There is also the latent models, which is this thingy that I said, that you have an output, and you assume that there is like some hidden interaction, and you want to understand like the distribution of this interaction. And I mean, normally you can use the MLE, right? But this, you cannot enumerate all the possible interactions. And we know in the base problem, the marginal depends on the integral. So it's kind of, and if it's discrete, it's exponential. Like all the possible, because it's the sum over all possible probabilities. So you cannot do that, right? So what we do is we use an algorithm called EM, expectation maximization, in which we approximate both at the same time. So instead of minimizing the posterior, you minimize something called the elbow, which is this formula of here, right? And you first have to like initialize the probabilities, then you compute the expectation, and then you maximize, and so on. You repeat this process. And then there are latent positional models, and then latent block models, and I mean there are so many things. But yeah, this is the summary.